Students are often taught a highly specific explanation for how a microwave oven works. The device emits radiation that perfectly matches the precise quantum resonant frequency of the water molecule. Because standard kitchen microwaves operate at a defined frequency of 2.45 gigahertz, it is easy to assume this exact number was chosen to strike a natural harmonic inside the food. This comparison graphic shows the divide between that theory and the physics. On the left is the resonance myth, where waves excite a clean quantum state. In reality, as shown on the right, liquid water heats through a messy, classical process known as dielectric loss. Instead of hitting a sharp quantum resonance, the oven's oscillating field drives a hindered, frictional rotation among the crowded water molecules. Assuming that microwaves operate via a precise quantum resonance fails to account for the thermodynamics of liquids. To see why, we have to calculate the actual energy involved. We can determine the exact energy of a single microwave photon using the standard equation, energy equals Planck's constant multiplied by the frequency. This scale bar places that calculation in context. At 2.45 gigahertz, one microwave photon carries about 10 microelectron volts of energy. Compare that to the large red sphere, representing ambient room temperature thermal energy, which sits at roughly 0.026 electron volts. A single microwave photon is 2,600 times weaker than the background thermal noise already present in the room. At this scale, the photon lacks the energy required to break a chemical bond or promote an electron to a higher state. Microwave heating cannot simply be a single photon absorption event in the way that visible or ultraviolet light interacts with matter. Because individual microwave photons are incredibly weak, the temperature rise we observe in food requires the collective macroscopic absorption of enormous numbers of these low-energy photons. To map how that macroscopic absorption happens, we start with the structure of a single molecule. A water molecule has a bent shape, pulling negative charge toward the oxygen atom and leaving the hydrogen atoms slightly positive. This creates a permanent electric dipole. When an external electric field is applied, physical torque forces the molecule to rotate and align with the field lines. The quantum mechanical equivalent in the top right describes how the time-dependent microwave field couples directly to the molecular dipole. If we place a single, perfectly isolated water molecule in a microwave field that alternates direction billions of times per second, the molecule will rotate to follow the field exactly. But perfect alignment produces zero net heat. The molecule acts like an ideal spring, temporarily storing energy as it aligns, and then returning that exact same energy to the electromagnetic field as the field reverses. The ideal spring scenario only applies in a vacuum. A cup of liquid water is a dense, highly interactive environment. This chart compares absorption states. On the left, isolated gas phase water molecules exhibit clean, strictly quantized rotational energy levels. On the right, liquid water molecules are trapped in a cooperative network, constantly colliding with neighbors and forming temporary hydrogen bonds. These intense intermolecular forces completely smear out the clean rotational energy levels, obliterating the sharp spectral lines entirely. The microwave field does not trigger distinct rotational quantum jumps in the liquid. Instead, it forces a broad, sluggish, and highly hindered collective reorientation. When an electric field is applied to this crowded environment, the dipoles take a measurable amount of time to reorient. Physicists call this delay dielectric relaxation. Because of constant collisions, the molecular polarization falls out of sync with the electric field, creating a specific phase lag. The field continuously pulls against molecules that are out of phase, forcing it to do net, irreversible work on the liquid. We calculate the resulting heat using the Debye relaxation model. This equation for absorbed power isolates the dielectric loss factor. This factor is the exact mathematical measure of how effectively a material converts that phase lag into dissipated energy. The entire process requires friction. The heat cooking your food is the chaotic kinetic energy born from water molecules failing to follow the field perfectly. We can test the dielectric loss model by applying it to an edge case. Why a block of frozen food heats so poorly in a microwave? This structural diagram explains the crystal lock effect. Freezing locks the water molecules into a rigid hexagonal lattice, severely restricting their ability to rotate. Without the ability to freely rotate, the dipoles cannot lag behind the electric field. The dielectric loss drops to near zero, allowing the microwave energy to pass straight through the solid ice. However, any small pocket of liquid water within the food does experience dielectric loss. That liquid heats rapidly, melts the adjacent ice, and creates thermal runaway, resulting in extreme hotspots right next to frozen cores. Adding salt introduces a second major heating mechanism. In soups and saltwater, the oscillating microwave field physically drags dissolved sodium and chloride ions back and forth, generating intense conductive heat loss. The physical state and chemical composition of the material entirely dictate how the electromagnetic energy is absorbed. Quantum resonance is irrelevant to the outcome. We can now trace the complete thermodynamic energy transfer chain, from the oven to the temperature rise. First, the coherent oscillating electric field penetrates the liquid. It couples directly to the permanent molecular dipoles, exerting a continuous torque on the water molecules. Second, the crowding hydrogen bond network resists this applied torque, causing the physical polarization of the molecules to fall out of sync with the electric field. Finally, this phase lag generates dielectric loss, dissipating the driven rotational energy through countless molecular collisions. A microwave oven does not rely on a precise quantum harmonic. It operates entirely on the thermodynamic friction of liquid water, fighting against an oscillating electric tide.